Now that you have a sense of what position is, what velocity is, what acceleration is, and how they're all sort of connected, how their units are connected, how their formulas are connected, we're going to try and talk about how their graphs are connected. So there are three types of graphs we often do in 1D kinematics. We've seen some examples of position time graphs and velocity time graphs already. And today, for the first time, we're going to bring acceleration time graphs into the mix. And what I want to highlight here right off the bat is that there are important relationships between these three graphs. That's sort of the theme of the last couple of lessons, is that there are relationships between all these things. In the last lesson, we talked about how velocity was the rate of change of position, and acceleration was the rate of change of velocity. Right? An object sitting still has position, but if its position changes, it has velocity. And it can keep that velocity as much as it wants, but as soon as that velocity changes, it has acceleration. We also talked about units. This is measured in meters. Velocity is in meters per second. Acceleration is in meters per second per second. So the connection between these graphs is if I'm looking at one of these graphs and I want to get to the next one. If I'm looking at a position time graph and I want to know what an object's velocity is, I look at this graph and I find the slope. So I can get from here to here by taking the slope. And as you might be starting to expect by now, with all these patterns, I use the same process to get from here to here. If you're looking at a velocity time graph and you want to find acceleration, you take the slope. Now, we can also go back the other way. This involves an idea that's a little odd when you first learn about it. It turns out sort of the opposite of a slope is an area. So if I have an acceleration time graph and I want to know how much an object's velocity is changing, I find the area under this graph. And if I'm looking at a velocity time graph and I want to know how much something's position has changed, I find the area under this graph. That'll tell me how much this guy has changed. Now, I've sort of described this as being a first lesson in calculus. Calculus is not a course most of you will do in high school, although some of you might take it in your grade 12 year. But it's a really important topic in math. It's pretty complex compared to some other topics. It has a bit of a reputation. And if you asked a lot of people to sum up what calculus is in sort of like, less than 10 words, a common explanation you'll hear is that it's the study of slopes and areas. So that's why I call this sort of a first lesson in calculus, because we're looking at slopes and areas, and how we can go one way using a slope and the other way using an area. We're not going to actually have to use any calculus today, so don't worry. We're not going to be learning university level math. But the ideas we're working with today are some of the same ideas as are used in calculus. And if you're interested, the special name in calculus for taking the slope of something, it's called finding the derivative. And the special name for finding the area under a graph it's called finding the integral or taking the integral. These words are not important for this course. I just throw them out there because it can be interesting, and you will see these words again later. If you take calculus in high school, you'll probably mostly be doing derivatives, and you might do a few integrals in the course. And if you take it in university, generally there's one semester where you focus on doing these, taking slopes, and one semester where you focus on this, finding areas. This idea of the area under a graph is a bit weird. It's not obvious necessarily to students when they see that phrase, what that means. So I'll clarify it a little bit here, then we'll do an example on the next page. Area under the graph means the area between the graph and the x-axis. Okay, so what we're going to do is we're going to look at a set of some graphs where I have a position graph, a velocity graph, an acceleration graph. And we're going to try and use the information in some of these graphs to fill in the others. Okay, so there's sort of two separate questions here. One question is over here on the left side. A separate question is over here on the right side. I think of this as question 1 and this is question 2. Now this first graph, I want to note, this is actually a position time graph. The place I got this from, they use this letter D for position. We don't use D for position, we use it for distance or displacement. But I want to be clear, this is a position graph. Similarly with this one over here. Okay, so in this first question over here, I have a position graph given to me and I want to find the velocity graph. Well, I know to get from a position graph to a velocity graph, I take the slope. So if I look at this guy and I find the slope of this graph, that tells me what the velocity will be. The slope of position is the velocity. So let's start by looking at this first part. The slope here is the same for this whole section. Remember, slope is the steepness of a line. This line always has the same steepness. It's not getting steeper or less steep. So I've got one slope, the whole first section here, which means I have one velocity, this whole first section. What is that velocity like? What is that slope like? Well, I would say this slope is a positive slope. Remember, positive slopes go like this. A slope of 0 is like this. And a negative slope goes like this. So this guy is definitely a positive slope, and it's staying the same for this whole section. So that means the object's velocity is positive, so somewhere up here. And it's staying the same for the whole section. The slope of position is velocity. Let's look at the next section now. Here, again, I have a positive slope. Again, the slope is staying the same the whole time. But this slope is less than this slope. This guy is not as steep as this. So my velocity is positive. It's the same this whole section, but it's a smaller velocity than I had here. So when I draw that, I could draw it like this. My velocity is still positive, right? It's up here, above the x-axis. It's the same for this whole section, but it's smaller than the velocity I had over here. Okay, so that's going from position to velocity. Note that what I do to get from position to velocity is the same as what I would do to get from velocity to acceleration. Take the slope in both cases. So let's look at this next problem now. Here, I have a velocity graph, and I want to get to acceleration. So if I take the slope of velocity, I get acceleration. what can even be useful for some of these is to write some notes down to yourself. We sort of noted a few things about this graph, but we just kept them in our head. We said, oh, this slope is positive and it's staying the same the whole time. We'll do the same idea over here, but we're going to write those things down. So because I'm interested in the slope of velocity, because that tells me my acceleration, I'm going to write down some notes about the slope of velocity. So one thing I notice at the first section, the slope of the velocity here is 0. And it's 0 for this whole section. Remember, we said lines like this had positive slope, lines like this had a slope of 0, and lines like this had a negative slope. So this guy is a slope of 0. Now for the second section, my slope here is negative. That is a negative slope, and it's the same slope everywhere I go. This line doesn't change its steepness. It doesn't change its slope. So the slope is negative and constant, staying the same. And then in the final section, I again have a slope of 0. Now, the reason I've been writing down some notes about the slope of velocity is because the slope of velocity is acceleration. So everything I wrote down here about the slope of velocity can also be said of acceleration. The slope of velocity is acceleration. So when I draw my acceleration graph, what does it look like? Well, it's going to start at 0, and it's going to stay at 0 for that whole first section. And then in the second section, my acceleration is going to suddenly become negative and stay constant at that negative value for the whole middle section. So my acceleration becomes negative, stays at that same negative value for the whole middle section. And then for the third section, my acceleration jumps to 0 again. There's my acceleration time graph. Now we're going to do the tricky one where we go backwards. We start with the velocity graph and we will get to the position graph. So, what's the relationship between velocity and position? Well, the slope of position is velocity. So, I'm going to write down some information about the velocity. And that'll help me figure out what the slope of my position graph is. So what do I know about the velocity here? Well, this velocity, remember I'm graphing velocity. So I'm really just looking at the value of this graph. Where am I, on the x-axis? I start up here where positive numbers are. Negative numbers are down here, positive are up here. So I start on a positive number and I stay the same. The velocity is positive and it's constant. Okay. Then in the middle section, my velocity decreases and even becomes negative. It starts positive, then it goes to 0, then it goes negative. I'll write that. It goes from positive, then it goes to 0, then it goes negative in my middle section. And in my bottom section, my velocity is now negative, right? We're down here below the x-axis, but it's staying at that same negative value. It is negative and constant. So the whole idea here was if I looked at the velocity, that would help me figure out my position, because the slope of position gives me velocity. So everything I've written about velocity is also true about the slope of position. So now I have to graph position. I have to graph something whose slope is described by these adjectives. Now the weird thing here is I have no idea where this graph starts. I don't know if the position is 0. I don't know if the position is positive. I don't know if the position is negative. I can start it anywhere I want here. All I know is what the slope of this graph is like, but I have no idea where the graph is. So I'm going to start off with a slope that's positive and constant. And randomly, I'm going to just decide to start here. So my slope needs to be positive and constant. Remember, positive slope looks like that. So that's what my graph should look like. Slope, positive, constant. Slope is not changing. The steepness is not changing. Now in this middle section, my slope goes starts positive. Then my slope becomes 0. Then my slope becomes negative. So at the beginning, my graph's going to look like this, a positive slope. In the middle, my graph's going to look like this, a slope of 0. And at the end, my graph's going to look like this, a slope that is negative. So here I am. Positive slope, 0 slope, negative slope. I kind of have this nice curve. And for this last section, right, my velocity was a negative number and it was constant. So up here, my slope needs to be negative and constant. So a negative slope means it's kind of angling down, and the slope is constant, meaning the slope doesn't change, the steepness doesn't change. And again, whether I drew this, I could draw this whole graph up higher or lower or anywhere up and down that I wanted. It would still be correct, because all we know about is the slope. We don't know where it starts. Let's shift gears now and look at this second idea here. This idea of finding the area under a graph and how that can help us figure out or calculate some of these things like the change in velocity or the change in time. So let's do this with a couple of examples. An object in motion has the following velocity time graph. Calculate its displacement at 1, 2, and 3 seconds. Remember, displacement is the change in position. So basically, we have here a situation where we're looking at a velocity time graph. We want the change in position. So we're finding the area under this graph to see how this has changed. So, if I want to know how much the position has changed after 1 second, I need to find the area under the graph up to 1 second. And remember, we said the area under the graph means the area between the graph and the x-axis. So for this first second, to find the displacement or the change in position, I'm trying to find the area between the graph and the x-axis, meaning I'm trying to find this area here. Okay, so for that area is, this object is a triangle. Area of a triangle is 1/2 base times height. The base of this triangle is 1, and the height of this triangle is 1. So I have 1/2 of 1 times 1, which is 0.5. So the area under the graph between 0 and 1 seconds is 0.5. So that means the displacement after 1 second is 0.5 meters. Now, if I want to know the displacement after 2 seconds, so from the time the object started to 2 seconds later, now I'm looking at this big area here. So I've got a much larger shape. And I want to know the area of that triangle. So again, area for a triangle is 1/2 base times height, or base times height divided by 2. This large triangle for the first 2 seconds has a base of 2, right, from 0 to 2, and a height of 2, from 0 to 2. So its area is 1/2 times 2 times 2, or 2. So the displacement of this object for the first 2 seconds is 2 meters. Now this might seem a little weird. How come the object covered so much more distance, more displacement, in the first 2 seconds than it did in the first 1 second? This is only twice as much time, but it went 4 times as far. Why is that? Well, if we look at the graph, we see what the object is doing. Remember, this is a graph of velocity. Its velocity is getting bigger and bigger and bigger. Velocity starts at 0, then it goes to 0.5, then it goes to 1, then it goes to 1.5, then it goes to 2. So this object is going faster and faster and faster. So in the first second, it covers a little bit of ground because it's going pretty slow. But in the next section after that, it's covering a lot more ground because it's going a lot faster. So it makes sense that the distance covered for the first 2 seconds is quite a bit more than the distance covered for the first 1 second. Now, we're also being asked for the displacement after 3 seconds, which means I want the whole area of under this graph, the area between the graph and the x-axis for the first 3 seconds. And the first 3 seconds is basically this green triangle, which I already calculated, plus this red rectangle. So I'm going to do, write that over here. We got my green triangle plus my red rectangle. The green triangle, we already said, had an area of 2. Right? That's the number we calculated here, so that's the area of my green triangle. And my red rectangle, well, area of a rectangle is just length times width, or base times height. Length of this triangle, or base of this triangle, it goes from 2 to 3, so that's a base of 1. The height, well, it goes from 0 to 2, so that's a height of 2. So the area is 1 times 2, or 2. So if I've got an area of 2 here in the green triangle, and an area of 2 here in the red rectangle, my total area for the first 3 seconds is going to be 2 plus 2, or 4. You might be thrown off a little bit by these units here. Why am I using meters for area? Shouldn't area be in like meters squared? Remember, we're not talking about the area of this paper or the area of this shape that I've drawn. We are finding the area of a shape, but it represents something else. Because we're on a velocity time graph, when we take the area, it represents position. So it's not, the end goal here is not to find like the area of this little chunk of paper. I do find that, but because that represents the change in position. So that's why my units are the units of position. Okay. Just going to add some color up here as a reminder of which colors I used for which parts of this problem. Okay, let's do our one last problem. For the following velocity time graph, calculate the total displacement and total distance. Okay, well, first of all, what's going on a bit different in this graph is I have some negative velocity here. Positive velocity is up here, negative velocity is down here. Here's 0, so this is actually my x-axis, right there, right where 0 is. That is my x-axis. Okay. So to get displacement or change in position from a velocity graph, I have to find the area under the graph. So area under the graph, remember, means the area between the graph and the x-axis. Here's my graph. Here's my x-axis. I want the area between those two. So I'm trying to find this area here. Between the graph and the x-axis. Well, these are two triangles. Formula for the area of a triangle is 1/2 base times height. 1/2, this base has a length of 1. And the height of this triangle is 3. So that gives me 1.5 meters. And the area of this guy down here has a base, goes from 1 to 2, so that's a total distance of 1. And its height goes from 0 to -3, so that's a total height of 3. Also 1.5 meters. But there's an important point I'm going to tell you here that you got to remember. And that's that when we're using areas to represent changes in position or changes in velocity, they can be negative, right? A change in position can be negative. Position can go backwards. A change in velocity can be negative. A velocity can become smaller. So although we don't normally think of like the area of a sheet of paper as being negative, because these areas represent other things, we can interpret them as being negative. And so any area under the x-axis is interpreted as being negative. That's a key point. Area under the x-axis is interpreted as being negative. So this I'm actually going to put as a negative 1.5. These are my final answers, but they're important pieces of information, so I'm putting boxes around them. So let's see if this makes sense sort of intuitively. What's going on in this graph? Okay, I have velocity. Velocity of this object starts positive, and then it slows down. The velocity goes from 3 down to 2, down to 1. The velocity goes to 0. So this object is moving forward, positive velocity, but it's slowing down. And after it stops, the velocity becomes negative. It starts moving backwards, and it's moving backwards faster and faster. So the object, did something like this. It's moving forward, slowed down, and then it started moving backwards, faster and faster and faster and faster. So in this first part of the graph here, we're looking at the forward movement. And in the second half, we're looking at the backward movement. So this 1.5 meters, that's the displacement while it was moving forwards. And this negative 1.5 meters, that's the displacement while it was moving backwards. So if it moves 1.5 meters forward and then 1.5 meters backwards, it's going to end up back where it started. And since displacement is a straight arrow from start to finish, an object that starts and finishes in the same place has a displacement of 0. So I've got a positive 1.5, that's that displacement, and then a negative 1.5, that displacement, equals 0. The displacement of the object is 0. Now the question also asked me for the total distance. Now remember, distance depends on the path the object took. It doesn't just depend on start and finish. So here we have to use our intuition a bit. Well, if the object moved forward 1.5 meters and then backwards 1.5 meters, those amounts would sort of add together. Distance can't really cancel out. It doesn't matter how far you drive your car and in what direction, the odometer never goes down. The total distance you've driven your car can only go up, even if you're moving in a negative direction. So for displacement, I took positive 1.5 and negative 1.5. For distance, I actually just add positive 1.5 and positive 1.5. It doesn't matter if I'm going backwards, I'm still adding more distance. So those are my final answers. This object's distance that it traveled was 3 meters, and the object's displacement was 0. And the key idea here is, well, there's a couple key ideas on this page. I would say the three key ideas we've talked about are, when you're looking at a velocity time graph and you want to know how something's position has changed, you find the area under the graph. Area under the graph means the area between the graph and the x-axis. Right? Graph, x-axis. Here's the area. And if we have an area under the x-axis, like over here, we interpret that as being negative.